Hi, everybody. Sorry about being late today. Let me wind down the music here, and we'll get started. Let's look at the administrivia real quick. So, lab worksheet number 1, I'm getting all sorts of questions about that. That is due tonight, with regards to last call, so get that worksheet in. I will be pretty busy tonight, so please do not, send me a question at like 11:30 and expect a quick response because, oh, excuse me. Sorry. Don't expect a quick response on any questions about the lab because I have other things that I need to attend to tonight, and I will get to any responses that I can. But if you have questions about it, make sure that you check the Discord. If you send me an email this morning, I haven't checked it yet. I'm going to try and get to that after class because I have 30 minutes to do all my email. But today is kind of a busy, hectic day, and so is tomorrow. Tomorrow I'm actually getting my second vaccination. So the whole week for me is basically just going to be like, I'm trying to get everything done today in case like tomorrow and Friday are awful, and I'm incapable of doing anything then. What else do we got here? The quiz for Chapter 1 is due today. Make sure you get that in by the deadline, too. That is a soft deadline. If you've turned it in on Thursday, that's no problem. We're probably going to finish up Chapter 2 today. Oops, I didn't mean to click that. So that quiz will be going up tonight as well. So let's talk about some isotope notation. We left off on the concept of isotopes yesterday. We were talking about how atoms have various parts, and those parts were discussed and discovered in various experiments. So we had the cathode ray experiment that discovered the presence of a charged particle that was mobile. That was the electron. We have the oil drop experiment that determined how much charge was on an electron. And then we had the Rutherford's gold foil experiment, which determined the presence and rough size of the nucleus relative to what ideas were held at the time. And then later on, we talked a little bit about Marie Curie and how she did experiments with radium and how different isotopes arose from that and gave credence to the idea that, oh, there must be a neutral, non-charged particle also in the nucleus, and that's called the neutron. We're going to write some symbology to identify the parts of the atom in a shorthand notation sort of way. So the first symbol we're going to use is Z. Z is the atomic number, and it is the number of protons. We're going to use Z a lot in this class in Chapter 3 when we start talking about Z effective and stuff like that. So make sure that you remember that abbreviation. A doesn't really get used as much. A is the number of protons and the number of neutrons added together. It's called the mass number. Something to note is that Z appears on the periodic table. A does not. So the periodic table has the atomic number. That is the top number in the cell for the element that you're looking at. And depending on which periodic table you're looking at, if it's P table, it'll probably be on the top left. I'm looking at a Web Elements one that I had photocopied and laminated. And it's in the just top center. But it's universally, the number at the top is some integer, and that is the atomic number. A, however, does not appear on the periodic table in any form. Please do not mistake A for some other number. All right. Now, if the atom is neutral, then you know that the number of protons and the electrons are equal. So Z is also a count for the number of electrons, but only for neutral atoms. So be aware of how many electrons are present in whatever species you're looking at. And know whether you are looking at an element or an ion. what we're going to do is we're going to put all that information together, and we're going to make some symbols. So the first thing we want to do is we want to look up the element symbol for whatever species it is that we're looking at. And so we do need p-table for that. Let me get p-table out real quick. There we go. So that's in the chat that you can use now if you'd like to. I lost my slide. There it is. Okay. So we're going to describe any element in this manner. On the board here, I have curly brackets E. We're going to replace that whole thing with whatever the symbol is for the element that we're examining. So if I was looking at scandium, for example, I would replace curly brackets E with just S, capital S, lowercase c. Don't need any curly brackets. I just put the curly brackets in there because when I had just the letter E, people didn't replace E for some reason. All right. Next, we're going to write the atomic number. The atomic number appears as a subscript in front of the chemical symbol. Now, you might think that's a little bit redundant because if, for example, I wrote scandium, scandium's atomic number is 21, so I would write this down here. I could never put 21 in front of any other thing because that wouldn't be scandium, right? If I had titanium instead, its atomic number is 22, so I'd have to do something like this. I could not do this because this doesn't make any sense. So in a lot of texts, the atomic number is omitted because the symbol does that task for you. So just be mindful that not everybody writes the atomic number in front. For our purposes, I'm going to ask you to do that. The next thing that you do is you write the mass number. You sum the number of protons together with the number of neutrons. And whatever that number is, you write it in the position as a superscript before the chemical symbol. That's your A. Z and A should be both integers, so make sure that you, again, are not copying numbers off the periodic table because that's incorrect. Don't do that. If you are looking at an ion, in the top right of your symbol, the superscript after you've written symbol, you're going to indicate the charge. The correct notation to write the charge is to write the number first and then the charge symbol, positive or negative. If you write this, oh, it's iron plus 3, people are going to think, oh, you must play Dungeons & Dragons. Haha, you're a nerd. And the last thing that you want is for scientists like chemists who spend all their time in a lab calling you a nerd, right? We don't want other scientists to laugh at us. So do this the correct way. Put the number first and then the symbol. For what it's worth, D&D is awesome and I am totally a nerd, but screw those other chemist guys, right? The last thing you have to do is celebrate, because that's what you want to do after you've done this correctly. So this symbol right here is called complete chemical symbol notation. You may also hear it called isotopic symbol notation. I just write it as ZAE or ZA notation. I personally just made up this label, but it only is 3 letters long as opposed to like 26, so I like that description. So let's do an example. I'm going to give you a carbon atom, and my carbon atom is going to have 6 protons, 6 neutrons, and 8 electrons in its in it, I guess we'll say. I almost said in its shell, but that's not quite right. So, all right, so what is Z? Well, if Z is the number of protons, that's this. So we would go like this. Whoop. And then what would we do for A? A is the number of protons. I lost my pen here. There it is. Protons plus neutrons. And so that would be 6 protons and 6 neutrons would be 12. So I would write that up here. And then finally for the charge, I need to look at the number of protons and electrons and compare them together. So I'm going to box these in here. So for charge, I have 6 protons and 8 electrons. If I sum these two things together, 6 plus negative 8, what I get is negative 2. So that would be the charge on this ion, and I would write it with the number first. So if you have more electrons than protons, you'll have a negative charge. If you have fewer electrons than protons, you'll have a positive charge. And the way that you can calculate charge, just in case you were curious, is protons plus electrons, but use the charges. All right, so there's our symbol. 12,6 carbon with a negative 2. Another way that you may see something like this written, you can't import the charge this way, but what you can do is you can write something like this, carbon 12. And when you write an atom in this manner, the number that you write after it is the mass number. So you might hear things like iodine 127 or cesium 131 or cobalt 60 or whatever. That number that is given is the mass number. And if you're writing a sentence, it makes a lot more sense to write out carbon-12 or carbon-14 or whatever it is for the isotope you're talking about, rather than try and typeset all of these subscripts and superscripts on top of each other. All right, so those are various ways that we can identify atoms and then describe them using this sort of term. I accidentally hit back. There we go. So what I want you to do, for the top 3 problems there, I want you to write the isotopic notation symbol for each of these scenarios, we'll call it. I've tried to make them a little bit of a puzzle. Make sure that you are carefully considering the information that's presented. And then down at the bottom, what I want you to do is fill in this chart based on all of the information that you see here. So, for example, in the first row, you see that it's chromium. How many protons does chromium have? Well, you have to go to p-table to look that up, and you can fill that in. How many electrons does it have? Well, it have the same number of protons. However, it has a charge of 4+, so that should help you. So, fill in that table, do those ZAE symbols on the top, and we'll go over the answers together in just a bit. These are really difficult to type into chat, so when you're done, just say, like, you're finished or whatever. And we'll go over the answers in about 2 minutes or so. All right. Let's go over the answers here. So, now with the highlighter, we need a pen here. All right, so this first one right here, an atom with 7 protons. So I'm going to write it symbol. I'm going to write them up here. So 7 protons is Z. We'll write that there. I'm going to go to the periodic table. I'm going to find which element has 7 protons. That is nitrogen. So there you go. I have 8 neutrons. So what that means is that if I add protons and neutrons together, 7 plus 8 would be 15. We'll put that up there. And then I have 6 electrons compared to 7 protons. 7 plus and 6 negative is a charge of 1 plus. So I'm going to put that up here. There you go. Excuse me. For this second one, note that I've already given you Z and A, so you just write those numbers right in here. Don't have to add them together. I have already done that for you. Now, we got to go find what element that is, so I got to go look at the periodic table. I need element 25, that's manganese. There you go. And it has a charge of 2 minus, so we'll just patch that right up there. There you go. And then this third one, an atom with the same number of protons, neutrons, and electrons, and A equals 36. Well, if we know that A is 36, then whatever Z must be, since this plus this gives you 36, each of these must be half of it, right? So that would be 18. And element number 18 is argon, and if there's the same number of protons and electrons, you don't have to write a charge up here at all. So there you go. There are the three symbols. Next, let's go to the table down here. So let's look up chromium. Chromium is element number 24. So it's got 24 protons. We'll put that in there. If I have 24 protons and a charge of 4+, I must have 20 electrons. Protons plus electrons in terms of charge would give you the charge that's left over. And then finally, if I'm going to write the isotopic notation symbol, I got to write Z on the bottom, A on the top. A would be protons plus neutrons, so that's 51, it looks like. This is chromium, so we'll do that. All right, the next one, 16 protons, 18 neutrons, so 16 plus 18 is 34. What element has 16 protons? That is sulfur. There you go, and we'll write its name in here. And then finally for charge, 16 protons and 16 electrons. No charge. Ag is silver. We'll just fill that right in there. Number of protons, boop, there you go. Number of neutrons is going to be, well, if 47 plus blank is 106, because that's A right here, right? I could just subtract these two, 106 minus 47 to get the number of neutrons. So that would be 16 minus 7 is 9. 9 minus 4 is 5. I believe that that's right. And then if I'm going to do charge, 47 and 46 would be plus 1. So nitrogen has a charge of -3 if we are considering what ion it forms. But for this given, I have thrown these random numbers together. This nitrogen has +1 charge because there's one fewer electron than protons. Now, if we let nitrogen do what it wants to do, it will adopt a charge of -3, and we'll talk about that in Unit 4, why that happens. But these examples, I'm just putting random numbers of protons and electrons together. Half of these things probably don't form. The silver one forms. The sulfur one, I mean, you can get elemental sulfur, yeah. Chromium, I don't remember if +4 is common. But yeah, anyway, the point is this is just for practice. So don't worry about whether these ions form or not. And try not to just get numbers stuck in your head for every situation, because these are conceptual problems. All right, let's talk a little bit more about isotopes. Now, you can make isotopes of atoms by just changing the number of neutrons. There is quite a wide range that you are allowed to do this with for most atoms. Some atoms only have one stable isotope, but for many atoms, you can have tons of different isotopes available. So what I'm going to do on the screen here is I'm going to put a bunch of isotopes of boron on the screen. The way that you can tell that they are isotopes is that if you look at the number of protons, they're all the same. But if you look at the number of protons plus neutrons, they're all different. And so the shortcut is same Z, different, that should have been an I, A. If you're looking at two different chemical symbols and they have the same Z but different A, what you are looking at are isotopes. Now, the term isotopes is kind of just a term that you should know so that when it is used colloquially, as in by like people who are on the news or whatever, talking about nuclear physics or nuclear power or something like that, so you don't get confused by it. There's nothing inherently dangerous about an isotope. Carbon-12 is the most common isotope of carbon, and you eat it every day. Anything that contains carbon, 99.9% of that is carbon-12. But it's an isotope! Don't let that worry you. Isotopes are just labels of things that exist, so. Now, some isotopes are dangerous, which is where the panic comes in. But you have to treat that on a case-by-case basis. For example, hydrogen-1, which is the most abundant form of hydrogen in the universe, is extremely abundant, extremely safe, because like it makes up all the hydrogen in your body, pretty much. Then you have deuterium, which is heavy hydrogen. You might have heard of it as heavy water. It's the hydrogen in heavy water. It's hydrogen with a neutron. So that'd be hydrogen 2. Both of those are safe. Hydrogen 3, however, is extremely radioactive. So that's tritium. Tritium is very unstable. So it depends wildly on the atom. Alright, so again, same Z, different A. I just dropped the stylus on the floor. Let me pick that up real quick. There we go. Now, many isotopes occur naturally. Many isotopes need to be created in the laboratory. Naturally occurring isotopes are called this if their half-life is greater than 4 billion years or so. Now, why did we pick this number? We picked this number because if something is naturally occurring, it needs to occur in nature. And in order for it to occur in nature, it needs to still be here. What that means is that when the Earth formed, roughly 4 or 5 billion years ago, I don't know the exact number, but it's about that many billion years ago, all of the elements that were present in the Earth were there at that time. And if they decayed away to nothing before today, before the present, we would no longer find or detect them. And so therefore, they would not be naturally occurring. Now, technically speaking, and if you've seen Futurama, if you've seen the episode of Futurama where the professor makes the time machine that only goes forward, it's actually factually accurate. At some point, everything will decay away to nothing. It'll take a very, 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 very long time, though. Like, far, far longer than we can even think of. And so, for a very, very long span of time, material that we are looking at is incredibly stable. So, like iron 56, super stable. Is it iron 56? Yeah, I think so. Carbon 12, super stable. So those things will last for extremely long periods of time. So long that it's very hard to actually detect their radioactivity, because it's just so infrequent, if it even occurs in our lifetime at all. Those are going to be naturally occurring isotopes. Now, other substances that have extremely short half-lives, or even relatively long half-lives, but just not on the order of billions of years, these are what we call synthetic isotopes. I'm trying to get a color here, so there we go. Synthetic isotopes are things that you have to make in order to observe. You can make any combination of protons and neutrons that you want to with effort. For example, if I really wanted to, I could do carbon-17. However, that may be too many neutrons. And what will end up happening is that this will decay into something else, like this. My neutron will turn into a proton and an electron, which is a thing that can happen. This is nuclear chemistry, by the way. So we don't actually study nuclear chemistry in this class, but when something decays, it'll turn into something that's more stable, and it keeps doing that until it lands on something stable. Uranium, for example, has this whole decay chain that ends up on lead. There's a lot of uranium in Earth, and there's also a lot of lead in Earth, and the two are related, it turns out. There are also other elements that decay to lead, and so lead is pretty abundant. In food labels, when it mentions contains potassium or iodine, is it always ions? Yes, because those elements have reacted. And we're going to talk about electrons and reactivity in Unit 3. We discuss electronic structure. And we'll show why all the potassium you find is K plus and not just K. Why are you meowing at me? Why? I think he's lonely. Do you want to say hi to the class? Say hi, meow. Resting. Meow. No, he doesn't want to say hi. He's shy. That's okay. I have one cat that's shy, and then Maya comes in, and she just wants to talk to everybody. Come here. You don't want to talk to the class? No. He just wants to brush against the computer. Do you want to say hi? No, he's just lonely. That's all. When we're dealing with atoms, we do not want to deal with their mass in a strict sense. So 1.994 times 10 to the minus 23 grams is a really obnoxious number to either commit to memory or to do math with, to punch in the calculator. Do not want, right? Now, the solution that we've come up with isn't exactly a lot better, but at least it deals with numbers that are roughly integers. So, we have devised something called the atomic mass unit. And the atomic mass unit is just a special unit, AMU, that is used to describe the mass of various things in our atoms. And then as a result, when we put those together, the mass of the combined atom itself. So, for example, a proton has this mass, really, really, really small. We're going to call that this many AMU. Now, in Chem 140, I rounded these numbers to just 1. And I said 1, close enough, 1, close enough, and then electron, 0, close enough. In this class, we're still going to not care about the electron because you need like about 1,600 of them, 1,800, 2,000 or something, for that even to be 1 AMU. And if you're going to get 1,000 electrons, you're going to have a substance that already has a lot of atoms in it. And so changing its mass by 1 is not going to be a big deal. So we're going to ignore electron mass for our purposes. But protons and neutrons make up a large portion of the mass of an atom. And so we do want to consider those to as low of a degree of, or sorry, not as low, as high a degree of precision as possible. Now, when atoms have been computed for their AMU, the electrons have been taken care of already. So I'm not going to ask you to put like 6 protons and 7 neutrons together and then weigh it and then just do the math and use these numbers. So these numbers are purely trivia, really, but it's just to show you that we have defined these numbers in this specific way. Now you might ask yourself, well, why the heck didn't you just pick 1 for the mass of a proton or the mass of a neutron or something like that? And it turns out that what we instead did was we did this. We set a standard of carbon 12. We're going to call this 12 AMU exactly. So that is an exact number. That is not measured. That is counted. That is defined. Infinite sig figs on that. And so from that, we can say, okay, 12 AMU is 1.994 times 10 to the minus 23 grams. And then we worked from there, and so we did the back calculation and found that protons were this number, and neutrons were this number, and so on and so forth. Now, why did we pick carbon-12 instead of protons? Well, it's hard to get just protons, but carbon-12 is easy. It's charcoal. It's graphite. We have that all over. You could literally go to the store and buy carbon. You just buy charcoal. There you go. That's carbon. So we use something abundant as our standard so that we can be sure that it actually is a standard. Now from there, once we've got the standard, this is our standard again, you can weigh any other atom based off that number. And so the way that we do that is by using a device called a mass spectrum. And the way that that works, I'll just show you the picture of this first. We'll come back to this example here. Here it is you're going to launch your material through a magnetic field, and it's going to either hit the center of the detector where the sensor is, or it's going to hit the edge where you get no result. And so what you do is you adjust this magnetic field. And if you increase the magnetic field, you can make it bend more. If you decrease it, you can make it bend less. And so what you'll do is first we calibrate it for carbon-12. We send it through the ionizer. The ionizer makes it an ion so it will interact with the magnetic field. And then it gets bent through. And we calibrate it to say, okay, I have detected carbon-12 at this magnetic field intensity. And so you can do the calculation and say, okay, this changing it by this much must mean that the mass is this number. And then you can get the mass of every other element or ion that you want out there to a very high degree of precision. Because we can manipulate the magnetic field very, very subtly. So we're going to come back and do that in a little bit. But for now, let's actually do some calculations to figure out other numbers relative to carbon-12 and also other elements. So if I put boron 10 through the mass spec, I get this result. Hey, this atom that you sent through is 0.83442 times the mass of carbon-12. So then we do the calculation, and this is the result that we get. And you'll notice that the mass number and the mass in AMU are similar, but not quite the same. In, I want to say, every case, if you rounded to an integer, you would get the mass number. I'm sure there's one case out there. I can't think of it, though. However, that said, you are off by a little tiny bit. And the reason for that actually has to do with relativity. You may have heard of this expression before. If you just jam protons and neutrons together and to make bigger atoms, you don't just sum their mass. Some of that mass gets converted into energy. This is how fusion works. So we can't just take the mass of 2 protons and the mass of 2 neutrons and add them all together to get helium-4's AMU. The actual mass of helium-4 is slightly lower, and the reason for that is because of this relativistic equation. And this is how the sun works, or how stars work. When you fuse 2 hydrogen atoms together to get a helium, the resulting mass is slightly less. The remainder is it's converted to energy. So we can't just rely on, oh, I'm going to do addition, because the result is, oh, these atoms don't quite work that way. Now, if you come at it from the other end and look at atoms that are too big, then you have to go in the other direction, and that's fission. When you break atoms apart, you get more energy out, as opposed to losing energy. Because it has to do with how binding energy per nucleon works, and that's nuclear chem, and I don't really want to get into that too much when I want to finish the rest of the chapter. But it is really interesting, and you can ask me about it after class. I can try and find references. I have a bunch of textbooks on nuclear chem. That was something I was interested in, was I was looking to do nuclear chemistry, and then the class that I took on it was so boring. Because there was so little to do. I think anybody can learn nuclear chem. All right. So now what we're going to do is we're going to take those numbers that we calculated from the mass spec. And now the other cat is here and she wants attention. Maya, no. Oh, no. She's going to sit here and meow at me. We're going to take all of the different isotopes that are available and naturally occurring, and we're going to determine the atomic mass. And what the atomic mass is this is the number that is on the periodic table for that element. So for instance, if we look at boron on the periodic table, it says, at least on my periodic table, it says 10.811. So what that means is that the average atomic mass of all the different isotopes that exist for boron that are naturally occurring, that average is 10.811. But in order to do that, we need to discuss how we get the average, because what if one isotope is more abundant than another? Then if we try and calculate the average, we would get a skewed result, and that would be kind of weird, right? So let's talk about how averages are calculated. So if you were going to calculate the average of anything, you would do something like this, right? So if I wanted the average of these, I don't know, these numbers, you would add them together and then divide by the number of numbers, right? And so you'd get whatever 30 over 4 ends up being, 7.5. Why is my alarm going off? Oh, it's my phone. Suspected spam. Okay, we'll hang up on that. All right, so that's how I get the average normally, right? Now, another way that you could write this expression right here would be in the following manner. I could move the 4 out front and do this, right? And then if I have the 4 out front, I could then distribute it to each term. And this might seem really stupid, like why would you want to do this? But it actually brings up a really important point. When we are doing an average, we give every number the same weight, right? These are my weights. Now, if we have the same weights for all these numbers, what that means is that they are equally likely to be selected. Now, if I'm just averaging 4 numbers, then of course they're equally likely to be selected. You can imagine me putting a 5, a 6, a 9, and a 10 in a bag, and the odds of you grabbing each one are identical because there's only one of each. But what if I didn't put one of each in there? What if I put 25s, 1,000 9s, and a billion 10s, and there were no 6s for some reason? The odds of you reaching in and grabbing something other than 10 are very low, right? So the average result that you would get would be much closer to 10, as opposed to, say, 7.5, which is what happens when it's statistically fair. With atoms, it's the same way. You don't have an equal distribution of isotopes. Instead, you might have, say, boron 10, which is 70% abundant, and then let me do it this way. So 20% abundant, and then boron 11, which would be 80% abundant. So what you would do to calculate the average mass would be, okay, I'm going to take its percent abundance times its mass, and I'm just going to write it like this. And then I'll do that for the other one. And then when I do the math, well, 20% of 10 is 2. And 80% of 11 is 8.8. And I'm playing fast and loose with sig figs here because I'm just estimating. And there you go. Notice that that's really close to the number on the periodic table. So, probably for boron, if there are 2 species, boron 11 is more common than boron 10. The formula for weighted average is this. So, the weighted average equals the percentage of whatever your first isotope is times the mass of that first isotope plus the percentage of whatever your second isotope is times its mass plus, and you just keep doing this until you've done it for every isotope. Now, to make your lives easier, you're going to want to express the percentage as a decimal. Then you don't have to worry about anything at the end. So when I punch this in the calculator, I just did this. You can't see that because it's off the screen here. But I just did this part right here. So I went 0.2 times 10 and then 0.8 times 11, enter, and I got 10.8. So that's what we're going to do to calculate average atomic masses. But my cat is meowing at me and I don't know what the hell is going on. So we're going to do that after the break. So here's the problem that we're going to do, which is almost exactly the problem that I just did really quickly. But I'm going to put, oops, that's not right. I'm going to put this on the screen here. We're going to take our 10-minute break. I'm going to see why my cats are yelling at me. I fed them, I watered them, I hugged them. It's never enough, is it? Alright, I will see you all in just a little bit. Once I get the music going. There we go. Yay! It's not often that I land exactly in 10 minutes. Alright, let's get back to it. So, on the screen here, I have the mass data for boron. So, we have measured that boron 10 weighs 10.0129 AMU. It is 19.9% abundant. Boron 11 weighs 11.0093 AMU and is 80.1% abundant. What I want you to do is use the formula for average mass, and so we'll put it on the screen here. Boop, there we go. We scroll it down a bit. And I want you to calculate the atomic mass of boron based on this formula right here. And we'll just go like that. So go ahead and do that. Type it in your calculator. It shouldn't take you very long. I need to go get a little bit more water because I didn't do that during the break. And when I get back, we'll go over the answer. Okay, so I'll see you in a bit. All right, so hopefully you've punched it into your calculator and got the correct calculation. But did you get the correct number of sig figs? Dun, dun, dun. So let's actually do the calculation and we'll see. All right, so we're going to multiply these numbers together. I'm going to write this as a decimal. Oops, that should be 0, 1, 2, 9. There we go. And then we'll do the same thing over here. 80.1% abundant times 11.0093 AMU. And so I'm going to do the multiplication first because it's in parentheses, and I'm going to write down that number. But that result will only have 3 sig figs, So when I did that, I got 1.9925671. I only get to keep 3 sig figs. And then when I do the next one over here, I also only get to keep 3 sig figs. So I got 8.82. Now I'm going to do my addition. So I got to set that up vertically. Oops, that's not the right number, though. And there's the answer I get. How does that compare to the periodic table? I don't know. It looks pretty damn close to me, right? Now, how do you get that next digit? Well, you would have to have more significant figures in your percentage in order to do that. The only way to get a higher number of significant figures in a percentage is to have a larger sample, and a larger and larger and larger and larger sample is required to get the next digit down for percentage. So some substances have a large degree of significant figures because we can get gigantic samples of them, like, for example, aluminum. Others, it's hard to do because there are many species in them that are radioactive, that changes the average, or where we get them, the sources from, they don't have the same isotopic distribution, stuff like that. So our degree of precision is limited by error. And that error can come from various places. All right, we're going to do this next example together because this one is a little more challenging. There are 2 isotopic or isotopes of chlorine that are abundant, chlorine 35 and chlorine 37. What is the percent abundance for each isotope? So let's look at that and show how to solve this problem, because there is an issue here. And the issue is that it feels like there's not enough information. But there is enough information, you just have to figure out how to use it. So I gotta scroll all the way up here. Okay. So first we want to write the weighted average formula for this. So the weighted average will be equal to, it's just whatever numbers on the periodic table for chlorine, right? So for chlorine, that would be 35.453 AMU. And that's going to be the percent abundance of chlorine 35 times the mass of chlorine 35 plus the percent abundance of chlorine 37 times the mass of chlorine 37. However, we're going to have an issue here. I could enter a number for mass chlorine 35 because we know that, but I don't have a number for percentage, right? Same thing over here. In fact, if I fill in all the numbers, here's what my equation looks like. I'm just going to truncate it down to 35 here. 34.9689. 36.9659. And now the issue becomes, well, how the heck do I fill in those two percentages? How would I solve this equation? I have one equation, but I have two unknowns, right? This underneath the line is my equation. Well, in the problem statement, I tell you this, and this is actually very important. What does that mean? At least in terms of these percentages right here. Any idea? Hopefully you're typing in right now or thinking at least that, well, yeah, there you go. They both have to add up to 100%, right? So 100% as a decimal is just 1. And now you have two equations that you can solve for the unknowns. So what I'm going to do is I'm going to go like this. This is now x, and this is now y. Remember in Algebra 1 where you would do stuff like this? And you had to solve for them using a system of equations, and you'd like multiply a row by some number and then subtract or substitute or whatever. That's what you have to do to solve this. So there is an algebraic way to do this, which I'm going to do. I'm going to turn all of that back into numbers in a second to show you the correct number of sig figs. But there's also, and I didn't have it up on the screen here, there is also this way. Da-da-da-da-da. So what we're going to do is we're going to type that equation. We're going to just put, oops, I messed up. Hold on. We're going to just put it into Wolfram Alpha. So here we go. 35.453 equals x times, oh, I need parentheses, hold on. X times 34.9689 plus y times 36.9659. So that's the first equation, semicolon. I'm just going to get rid of some of these extra spaces here because I don't know if they're needed or not. And then x plus y equals 1. Solve, please. Where's my solutions? There it is, right there in the middle. Right under where I stopped highlighting in blue. Solution, x is 75, y is 24%. Ta-da! So, way easier than anything that we'd have to do, but you're not going to get the right number of sig figs doing it this way. So, this is a good way to check your result. You just type it in Wolfram Alpha, and it will tell you the approximate answers. But now what I need to do... That's the wrong thing. That's the wrong thing. There we go. Now what I need to do is I need to show you guys how to do the algebra. So I don't want to write all these numbers over and over again. So what I'm going to do is I'm going to change my formulas to this. So there we go. And I am okay with keeping this as x plus y is 1. So we're going to do this. All right. So x is going to be percent 35 and y is going to be percent 37. So let's do the algebra. I'm going to take, this is equation 2, this is equation 1. I'm going to take equation 2. I'm going to do that. I'm going to substitute this into equation 1. There we go. So now I have one equation with one unknown. I need to FOIL this out. So that becomes this. Now, if this was an in-person class, this is what I would be making you do. So 1 times M37 is M37 minus M37 times X. I don't have any more factoring that I have to worry about, so I can get rid of these parentheses because now I can just rearrange. Anything that has an X is going to stay on the right side of the equal sign. Anything that doesn't, such as this, is going to get moved over to the left. Now I have two terms with an X in them, so I can factor that out. And that equals this, which hasn't changed. Oh, I made a mistake. Sorry, hold on. This sign right here is this sign right there. And then to solve for X, I just divide, so... There you go. Now you can just substitute in all the numbers. If I could hypnotize my students to do one thing, it would be to do all the algebra first and then put in all the numbers. It saves you so much time. I know what a lot of people are going to do. They're going to do this up here and write every single goddamn number over and over and over. Don't do it. Do the algebra. This looks like alphabet soup, but if you can get through it and recognize what's going on, then your ability to comprehend math improves so much. So let's look for the average mass of chlorine. So that's this, 35.453 AMU. Minus the mass of chlorine 37. That's on the screen there. 36.9659. Don't worry that that's going to be a negative number. It'll all work out because down here at the bottom, we're also going to get a negative number. All right. On the top of this expression, I'm going to subtract these two numbers. I have to set that up vertically. I'm doing it this way because when you do subtraction, you have to subtract the bigger number from the smaller number. But because the negative's in the wrong spot, my answer will be negative. That's just sort of my mental mnemonic for doing this mentally. So 2, 1, 5, 1. And then when I do sig figs, I didn't mean to. I don't get to keep this number. So this is the result that I get, which I would round to negative 1.513. I can do the same thing for the bottom. So we'll just do the subtraction. So 0, 15 minus 8 is 7, 15 minus 6 is 9, 8 minus 9 is 9, 5 minus 4 is 1. So I get that, and I get to keep all these numbers. So my result for X becomes this. These units finally cancel out. That's important because we have a percentage. Percent should not have AMU in it. It should just be a decimal, right? These negatives cancel out. That's also important. We need to have a positive percentage. And you get 1.513 divided by 1.9970, which, as you could probably estimate, is about 0.75, right? And so I get this. Provided that I did all of the subtraction correctly, which there is a real possibility that I have messed up on my subtraction. So, what did Wolfram Alpha say that the X value was? 0.7576. That's what we got. So that's a great sign. And then for y is easy. Y is just 1 minus x, right? So it's 1 minus 0.7576. So I'm going to get to go down to the 10,000ths place anyway. And that would be 24.24%. And there you go. Can you use a matrix? Yeah, you absolutely can use a matrix because a system of two equations can be solved basically using a matrix. That's what matrices are for, right? So I don't remember how to do like determinants and stuff because it's been 20 years since I've taken math. It was math 2C for me, or 2J or something. So you could absolutely use linear algebra if you'd like. I'm just showing you the regular old algebra. But yeah, if you want to use a matrix, go right ahead. All right. Not sure why I'm missing some decimal points on this one. Probably because I solved it the other way. An interesting feature about this is that depending on what substitution you get, we'll go back over here real quick. So here I substituted in y. So I said y was 1 minus x. Depending on which way you go, if I did x is 1 minus y, you may get a different number of sig figs. And that's because when you're done, you get all the way down here, your formula changes. Instead of subtracting these two terms, you subtract some other terms or something like that. And as a result, you get different numbers of sig figs. So just be mindful that that is something that can happen. If you have set this up in a different manner, you'll get a different number of sig figs than a different person. All right. So why is all of this important to us? Well, it's important because we are going to put all of these things into a mass spec to get this information, which we'll then use to do calculations like this. And so I explained how that works. Now, what you tend to do is you tend to put just a random sample of compound in there with all sorts of different isotopes, and you just slowly scan across all of the different masses that are available by increasing the magnet speed. And because you have this constant beam of ions hitting the detector, if you do that at a constant rate, you'll be able to say, oh, okay, at this mass corresponding to this magnetic field, I detected this many things. And then when you change it to this mass, I detected this many things, and so on and so forth. And the end result is you get something that looks like this. So what this is the machine was scanning across masses by slowly increasing the magnetic field to detect a higher atomic mass. And so it looks at 89 and says, oh, I didn't find anything. It looks at 90 and says, wow, boss, I found a whole bunch of stuff. And then it looks at 91. Oh, I found a little bit. And then at 92, and then 93, didn't find anything, and so on and so forth. Now, the y-axis on this is something that we append ourselves. The y-axis is what's known as the relative abundance. This is the percentage of these isotopes that exist compared to the whole sample. Now, in reality, this doesn't exist. You don't even really have a y-axis, you just have a count. But you can turn a count into a relative abundance really easily by dividing by the total number of hits, right? So, whether you see something that just says abundance and it's a percentage or not, you can calculate the percentage by just looking at something relative to everything else, and that's easy enough to do. Now, what the heck is this down here? We already know what the mass is, but why is it mass to charge? Well, when you shoot your ion through, so this is zirconium, so here's my zirconium. When it goes through the detector, it has to be an ion, or else when it gets to the magnetic field, nothing would happen, right? So if we make this an ion, and I'm just going to call it this for now, now it will hit the detector. But when I'm bombarding my sample, there is a chance that maybe I knocked off an extra electron. What would happen now? Well, it'd be doubly affected by the magnetic field, right? And so it wouldn't hit the magnetic field at this amount. So what this is saying is that, okay, your thing weighs 90 if the charge of it was 1. What would I have to do to make the detector see this one right here? I would have to make it be twice as strong. And so what would end up happening, or not twice as strong, twice as weak, I guess I would say. So this would be detected at this mass because its charge is 2 plus. Wait, is it 45 plus 2? I think so. The math doesn't make sense to me there, though. I feel like it should be 180 over 2, but... I'm going to have to think about that for a second, because I just confused myself. But anyway, if you have different charges, you will see these things at different masses. But there will always be one highest set where the charge is just plus 1. So if you have a plus 2 or plus 3 or something like that, you start seeing peaks. And I want to say that they're earlier, but now that I'm thinking about the ratio, it doesn't make much sense. So that's just sort of a curiosity, though. We're not going to be working with this. In fact, all I'm going to be doing for these diagrams is I'm going to give you this sort of thing, and I'm going to say, hey, tell me where on the graph this peak should be. So for instance, if you did, like, say, aluminum, and you got, I don't know what isotopes of aluminum even exist, so we'll do this one, this one, this one. And you did all the calculations, and you learned that there was this percentage, and then this percentage, and then this percentage. If you had to draw a graph of this, then it would just look like this. So 40, 50, 10. And that's really what I want you to learn from this is, can you read this graph and see what it means? That's good enough for me. All right, so again, the x-axis tells you the mass, the y-axis tells you the percentage. All right. I'm going to leave this example for you to do as practice because I'm starting to run out of time. I do want to try and finish the chapter today. I don't know if I can. But you can calculate the average mass of magnesium very easily by just multiply those two things together and then add all the results and then draw a picture of it. So I'll leave that for you to try. This last part does talk a little bit about the mole, and I do want to get through it. Let me see, how many slides do I have left? I probably won't be able to get through all this crap. Okay. We'll see if I can. A lot of it is pictures. We could go right through those. In Chem 161 and all of chemistry that you're going to be doing, you're going to see various ways of representing different molecules. On the left, those two, we're going to use those in this class. Actually, we're going to use the first three, I should say, in 161. The space-filling model will become much more relevant in organic chemistry because the space-filling model tells you where electrons live. But since we are very early on in the chemistry sequence, speedrun, right? Since we're very early in the chemistry sequence, we're really going to just concern ourselves with, hey, this is an easy way to represent the formula in terms of what's in it. Hey, this is an easy way to represent it in terms of what it looks like. Hey, here's what its three-dimensional model is. So those three are going to be the most important ones to us. Some elements come in pairs. It's very important that you understand how the number 2 is placed to get what result you intend to present. Putting a number in the front as a coefficient increases the quantity, whereas putting a number as a subscript after the element means that there is a bond going on between those two atoms. So if you mean to write H2, do not write accidentally an H with a 2 in front of it. That would be incorrect. Sorry, I thought I was going to sneeze there. I might still sneeze. Oh, no, I'm okay. Sorry. I don't remember what I was saying. My nose is itchy. Make sure you are writing the correct thing that you intend, is what I meant to do there. Which 7 elements are written with a 2 after them? It's these 7. So here's one of them. And there's the rest of them. So the 7 diatomic elements on the periodic table are these 7. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. The way that you remember these elements is that if you're looking at the periodic table, they form a 7. Like it looks like a block 7 on like a digital clock or something. The stem of that 7 is in group 7A. That's why they're the silly 7. Well, wait, why is hydrogen over here? He's silly. So that's the mnemonic I use to remember the silly 7, which 7 are diatomic. That'll be relevant to you in 162 when we start writing chemical equations, because you're going to have to turn a sentence like hydrogen and oxygen react to form water. And if you just write H plus O equals H2O, then you run into an issue. Some formulas that we will be using at some point, not really in 161, but more in 162. Writing the empirical formula is the simplest ratio of substances. We're actually going to do a little bit of empirical formula work in lab number... I want to say it's lab number 2 or 3. I forget which one. The empirical formula is important because when we do chemical analysis, really the only thing that you can determine about something is the empirical formula. I can't take an individual molecule and break it into pieces. So all that I see are just the pieces of billions of molecules left over. And when I compare the atoms of those, I end up getting something that looks like this. Not like that, but... So if this is like carbon and this is hydrogen, maybe my carbon looks like this. So I have this much carbon, but I have this much hydrogen. I regret drawing this many dots. And you could say, oh, okay, well, I can see that the ratio here is 1 to 2. So, okay, this must be the formula, something like that. So, the empirical formula is just the simplest ratio. Now, is the molecule actually CH2? Well, no. It could actually be this. This would also have the same ratio. Or it could be this. Or it could be any number of molecules, really. As long as the ratio from carbon to hydrogen is 1 to 2. If instead I had this, where the ratio was 1 to 1, that would also be obvious to tell, like, oh, now it's not any of these. Now it must be something where the ratio is, oh, say, 1 to 1. If I want to work backwards from this and find the empirical formula, I just divide by the common number that they have together. So in this case, it's 6. So this would be the empirical formula. So if I broke apart benzene, C6H6, I would get a bin with carbon and a bin with hydrogen, and they'd have the same number of pieces. Now, since I can only take apart a large quantity of molecules and not a single molecule, I can't learn about the formula by just looking at the piles, but learning what they are relative to each other is helpful. For something like this, again, you take the common number. So these all have 2 in common, but they also have 3 in common. They also have 6 in common. 6 is the highest one, so I'm going to divide by that. I get CH2O. For this last one, CO2, there is no common number. It's already an empirical formula. I can't divide out 1, so we're not going to do that. So sometimes the actual formula of a substance is the empirical formula. Not often for small molecules, but it's definitely possible. We're going to talk about isomerism a lot later in 261, and then a little bit later in this class in 161. Isomerism is not super useful to us right now, but it's in the textbook, so I will define it. An isomer is when you take something with the same formula and you connect it all in a different way. So both of these have the same formula, C2H4O2. But the molecule on the left, I have put the 2 carbons together, and then the one on the right, I've put the oxygen in between. So more or less, I have just swapped this and this around. The one on the left is vinegar. The one on the right is deadly. Changing the structure of your molecule can be very, 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 very critical in determining whether the molecule is dangerous or safe to consume. In fact, there is another type of structural isomerism where the structure is actually the same in terms of connectivity, but when you look at the molecules in space, you get a different result. So here I've circled some carbons. And if I circle that same carbon in the structure here, I'm circling it, but then I'm going to erase it so that you look at this. And you can see how the CH kind of comes out of the board there. In this case, it comes out and points the other direction. But if I were to rotate this entire molecule around 180 degrees, now this H that's pointing out towards us and to the right would then be pointing into the board. And thus would not be the same. I'm trying to point at it. It's hard to see here. Actually, I think I might have pointed... I'm pointing at the wrong H on this one here. It's this one. There we go. I'm pointing at the wrong H on all of them. There we go. So I'm going to draw the arrow along the H. That way you can see that. That might be a little more clear. So this is the same one. But now if I'm going along the H here, Now it's over here. No, that's not right. I can't see this goddamn picture. That's the problem. There it is. It's right there. I don't want to, like, skip over this topic and hand wave it. So let me get out mall view. Hold on just a second. I'm going to show you a better version of this. So I got to think of a chiral molecule, though. I'm trying to find it in here. Is this the one I want? Yeah, this is one of them. Can I get the other version, though? Oops. All right, did that work? Oh, this doesn't do stereochemistry, really? Oh, wait a second. Hold on. Okay, there we go. Yeah, okay. Sorry, I'm just trying to arrange these so that they are as spatially the same as possible before I capture it. Yeah, that'll work. Okay, cool. All right, so here's how isomerism works in space. Sorry that took so long. You'll see why this took a second from once I get this on the screen here. Okay, we're going to be using mall view a lot when we get to chapter 4. So on the screen now, you can see this structure. This is called thalidomide. Thalidomide was sold as an over-the-counter, like, morning sickness aid. And I feel like this is important enough to talk about because this is such a mortifying story. It turns out that even though the structure of thalidomide can be written in this way, if you look at the diagram over on the left here, I'm going to click this button, and you'll notice that the only change between the two diagrams here is this wedge in the middle, right? On this one, it's dark, which indicates that it's pointed up, and on this one, it's kind of dotted, which means it's going back into the screen. What this means is that the orientation of this bond is inverted, and so you can actually see that on the right here. So I have on the right here, I have, this is my nitrogen, and here I have my carbon with the hydrogen that points up. So this ring is sort of pointed in the down direction. This carbon nitrogen ring here is pointed down. But in this other example, it's kind of pointed up instead because the hydrogen is flipped in the opposite direction. So I'm going to just toggle them back and forth. And you can see the difference here, right? So there's the hydrogen pointing up. There's the hydrogen pointing down. I basically took the geometry and inverted it. But I didn't just spin the molecule because everything else is in the back, is in the same orientation. So there's that oxygen in the back. You could see that that's the same in both pictures, just kinked in a different way. Now, why is this isomerism important? Because one of these acted as intended. It was a cure for morning sickness. The other one caused severe birth defects. Dun, dun, dun. So, if you want to horrify yourself, you can type in thalidomide space babies. And you will get tons of pictures of people who were born from mothers who took this medication that was intended to help them with their morning sickness. And instead what happened is their children were born with like partially missing arms and heads. Like, it's terrible. And the whole reason that happens is because of the stereochemistry right here. These molecules look the same, but one of these just happens to fit the proper enzyme. So the whole point of this takeaway message here is that shape is really important when it comes to molecules. And when we get to chapter 4, we're going to spend the entire time discussing what is the shape of a molecule. Like, what's its geometry? What is the overall structure of this thing? Because when you get to biology, all you care about is shapes of molecules. And do they fit this enzyme? If they do, great, it will do this reaction. Maybe something you don't want fits the enzyme, and then it does some other reaction. Okay, now that is toxic. So, that's why I wasted 10 minutes trying to figure out this damn isomer thing, because it's actually really, really relevant, believe it or not. And it's hard to see in this picture because you can't see the hydrogens on my diagram. Well, I sort of just like, I made this bed, so now I have to lie in it, right? We're going to do the mole on next week because we're kind of out of time. So, quiz number 2 will be postponed. I will put it online once we finish Unit 2. We're going to finish Unit 2 next week on the first class session. And then we're going to do Unit 6. Let me check how much time I need for Unit 6 real quick, because I told myself if I needed more time, I could use Monday as an extra lecture. So we're going to do... Can I do this in 2 days? Oh, I don't do balancing chemical equations, so I absolutely can do Unit 6 in 2 days. Okay, cool. So we do not need to use the extra lecture next week. So there will be no class on Monday. We'll finish Chapter 2 on Tuesday. And then we'll get started on Chapter 6. Chapter 6 is quite short. And then what will happen is we'll start Chapter 3 in week 5. And we'll be in Chapter 3 for what will feel like forever. Because Chapter 3 is kind of the meat and potatoes of Chem 161. So that's where we're going. I want to thank everybody for coming to the lecture today. Apologies for the late start. Have a wonderful weekend, and make sure that you get all of that stuff in. Sorry, I'm just trying to get the outro theme. I never load the outro theme before I do the lecture. I really just should. There it is. All right. So, yeah, remember to get all those assignments in. Last call for lab number 1 is tonight. Quiz number 1 is due tonight. Last call for it is tomorrow. Take care and see you next week.